This question describes a nuclear decay resulting in the emission of a alpha particle and a gamma ray photon. Okay, but here right we can actually discuss this in a more general way. So let's discuss right what happens in a typical nuclear reaction. So suppose we have a X plus a Y, okay, turns into a W plus a Z, and suppose right we also have a gamma photon, gamma particle being released. Okay, so here right the Z could be thought of as alpha particle. Okay, because alpha particle is like also a helium nucleus. Okay, it's just another nuclide. So here right you see when we say that there's energy being released, so what does it mean? It means right here we'll have more mass, okay, and here we have less mass, okay, and therefore right energy appears on this the right hand side of the equation. Okay, and that energy right manifests in two forms. Number one right you see the energy release, okay, it manifests right as number one the gamma, and number two right a gain in Ke. So at the microscopic level right you mustn't think of energy being existing in a like a fluffy or a iffy kind of states whereby it's like just floating around, there's energy floating around kind of idea. There's no such thing. Okay, so whenever we say energy is released right we simply mean the reactants right have less Ke, but after the reaction right they end up having more Ke, they turn into the products and they have more Ke as a result of the reaction. Okay, so it simply means that the W and Z has more Ke than the X and Y. Okay, at the same time that there is a gamma being released. Why so? It's because of the mass energy conservation. So the mass right manifests itself as energy. Alright, so how do we write out the equation? Well, we'll take the difference, right? So the delta E is equals to the delta M, the mass difference. Okay, take note this is mass difference. Okay, there's another thing called mass defect. We'll go through it later on. Mass difference is always written as a delta M, whereas mass defect is written as a M subscript D. So this one times C square. Okay, so mass difference right in this case, if you want to just think about this as a absolute number, want to make this a positive number, right, then you simply take the bigger mass minus the smaller mass. Okay, so you'll be the mass of the reactants, so mx plus my, okay, minus mw minus mz, this whole thing times c square. Okay, so this energy right manifests as well. It manifests itself as the Ke of W plus Ke of Z minus Ke of X plus Ke of Y. So you see this entire term here right is the increase in Ke. Okay, then if there is a gamma being released right is plus a HF. Okay, so this term is like optional. It depends on whether the question mentioned there's gamma being released or not. Therefore right apply to this question, so you will see that the radium decays into radon right and the alpha particle and the gamma photon. So this guy right must have more mass. Okay, because after the decay it turns into two guys which have together right less mass after the reaction, therefore energy is released. Okay, so left hand side here gives you the delta m c square. Okay, and it's equals to what? HF, which is the gamma's energy. Then right you don't see a difference in the Ke here. Why so? Because right the initial Ke right was thought to be 0. Okay, because this is a nucleus right which is at a solid state in a rest states, right, so it's just not doing much. Okay, most of the time right initial Ke of the nucleus in a decay situation, right, it's always 0 1 because they are not doing much. Only when you talk about fusion, then you will talk about nucleus, right, with high Ke, because in a fusion you need them to have high Ke to begin with, to ram into each other, okay, to fuse. Yeah, but for decay or for fission, right, the starting Ke is usually just 0. Okay, therefore, right hand side is more like something like this one minus 0. Okay, so answer is D.